Stop 3, 3, 2, 1.
Ready? Okay, let's talk COVID-19 and some translational medicine applications. But before we begin,
3, 2, 1.
let's talk COVID-19 and some translational medicine applications. Before we begin into the details of some product concepts, let's first review the anatomy of the virus as well as the mechanism of infection. So this first slide is a CDC image of COVID-19, and you can see the focal point of our conversation is going to be this S protein, which is also known as a spike protein. These are the inverted red pyramids on this virus. And, you know, can we start over for a sec?
Yes, yes.
We're good?
Go.
Okay. Hi. Tonight's presentation on COVID-19 and some product applications is, give me one sec. We took something out of this deck. They just took it out, so I've got to figure out how to integrate it in.
Okay, 5, 4.
1 second. I got to figure out how to.
Okay.
What I'll probably do is I'll do it verbally, and that way, because give the listener some direction in terms of where we're going. Okay, got it.
5. Stop. 5, 4, 3, 2, 1.
Hi. Let's talk about COVID-19 and some potential product therapies. Before we do that, though, let's look at, well, that's great.
Okay. 5,
So
4, 3, 2, 1.
Hi. Let's look at COVID-19 and some potential interventions based on available science. But before we do that, let's first look at the anatomy of COVID-19, the mechanism of viral replication, and then let's look at some product applications based on evidence-based literature, as well as some internal developments which may be of value. So this first conversation will focus on the anatomy of the virus. And this first image is one that's been popularized internationally. And what I want you to focus on are the inverted red pyramids that are spike proteins, otherwise known as an S protein. And that is going to be the epicenter of a lot of our conversation as we explore viral anatomy and then the mechanism of replication, as well as the potential therapy points. This is a three-dimensional image of the spike protein that was published by Chinese researchers in mid-February. This is a schematic of the COVID-19 virus. And the focal points for our conversation really are the spike protein, as well as the RNA, which includes the genetic material for the virus. And then, of course, how does the virus bind onto the cell membrane, in this case, the ACE2 receptor? Now, when we look at the mechanism of infection for COVID-19, I'm actually going to defer to the SARS coronavirus from the 2002-2004 time window. Both COVID-19 and SARS 2004 are coronaviruses. They both bind onto the ACE2 receptor, and so we can use that 2002 SARS virus as a model for what is happening with COVID-19. So in this particular illustration, you have COVID-19 binding onto the ACE2 receptor at the cell membrane. And when that happens at this junction here, the virus is then pulled into the cell. At that point, the genetic material, which in this case is RNA, is brought into the cell for replication. That process of replication involves a number of thresholds. And the take-home here is that there's a genetic processing that takes place so that the virus can replicate, take over cell machinery, and in this case, increase its numbers exponentially to infect other cells in the body. When you look at COVID-19, it's relative to SARS 2002. It's interesting to note that COVID-19 has a very high affinity for the ACE2 receptor, much more so than SARS 2002, 10 to 20 times more so, which may, in fact, help to explain why it spreads far more easily than 2002 SARS. So here's a series of diagrams to essentially reiterate the mechanism of viral fusion. Here's the virus approaching the ACE2 receptor, and then the virus binding onto the ACE2 receptor, and then you move to viral fusion. All right, so let's talk about one of the potential therapeutic applications in our space, and that is humic acid. Humic acid was initially discovered in 1761 by Valerius, and the first published studies on humic acid were, yeah, we're gonna have to, can we slice and dice and splice? Oh, we can, okay. All right, so now let's talk about humic acid. Humic acid was first discovered in 1761 by Valerius, and the first publications started in 1786. Modern applications are predominantly in the oil and gas industry as a lubricant, and then of course there are applications in agriculture as a fertilizer. My colleagues from India know humic acid well because it has an extensive Ayurvedic application. So this next slide is intentionally brought in to illustrate what humic acid is not. So humic acid is frequently confused with humus, which is the soil layer just above topsoil. Humic acid is in fact something that needs to be mined. And it's mined from decomposed organic matter that dates back 280 million years ago to the Paleozoic coal age. When you combine decaying plant matter with water, microorganisms, and time, and you give chemistry an opportunity to do what it does, that decomposing organic matter turned into humic acid. And there are deposits across North America and other parts of the world. What prompted that layer reset? The transition that okay, got it. So how did we get here? There was essentially a global warming event at the end of the Paleozoic era, which resulted in a massive die-off of foliage across the world. That is the root supply for what has eventually become humic acid. And that interval of time is called the Carboniferous rainforest collapse. But with that collapse, you collected organic matter, which put under significant pressure, became the fossil fuels that we know today that fuel our cars and our industry. But we also got humics from them, as well as fulvic acids and whatnot, the humates. So when it comes to medical applications, sourcing is extremely important. And when sourced and processed correctly, humic acid has actually been found to inhibit viral replication. Let's start that over again. So sourcing is very important. And when sourced correctly, humic acid does an excellent job of inhibiting viral fusion. This is a 3D model of humic acid that is used for medical purposes. And by leveraging the three-dimensional options here, you can get a better sense for the bulk of this molecule. not working. It's not working. Oh, there it goes. All right, so then let's do that again. Okay. So let's take a look at what humic acid looks like. Here is a three-dimensional. Let's take a look at what humic acid looks like. What you see here is a three-dimensional model of humic acid that's been animated to help you appreciate both its size as well as its potential to, in this case, bind onto a virus and inhibit its fusion with the cell membrane. So the antiviral activity of humic acid has been studied by multiple universities and academic institutions, including the University of Southern California, the Southern Research Institute, Specialty Laboratory, and the National Institute of Health. And what all of those organizations found, based on their own studies, is that humic acid has antiviral activities for HSV1, HSV2, herpes simplex virus, cytomegalovirus, Epstein-Barr virus, influenza, and even hemorrhagic fevers. So if we focus on the literature exclusively published by the National Institutes of Health in 2002 and 2003, we can gain an appreciation for the antiviral activities of humic acid. This particular slide lists a variety of technical ideas. What I'd like you to focus on is the IC50 and the IC90. The IC50 refers to the inhibitory concentration, in this case of humic acid, that prevents infection of 50% of the cells. And the IC90 is the same idea, but applied to 90% of the cells. That's a way to calibrate the effectiveness of humic acid as an antiviral. So in this first table on the left, which looks at herpes simplex virus type 1, you see humic acid in the red box and a reference compound, in this case, the antiviral acyclovir, in the blue box. And you compare the IC50 and the IC90, and you can see that the humic acid concentrations are slightly higher than the acyclovir. But what's notable is that there is antiviral activity with this particular molecule. If you look at herpes simplex virus type 2 to the right, you see a similar phenomenon with humic acid in the red box and acyclovir in the blue box. But in this case, if you look at the IC90 and you compare humic acid to acyclovir, you see that you need a less amount of humic acid to achieve the IC90 than you do the reference compound acyclovir. Now if we look at varicella zoster virus, which causes shingles as well as chickenpox, you see a different story. Humic acid in red, acyclovir in blue, but in this particular case acyclovir is more effective than humic acid, but there is still efficacy, which is the take-home point. Similarly, with Epstein-Barr virus, you see humic acid in red and acyclovir in blue. And in this case, though, acyclovir is substantially more efficacious than humic acid relative to the other studies that I've cited thus far. This particular slide reviews various studies looking at different influenza strains. And what's notable here on table 8 is that humic acid has efficacy. Let's start that one over. On this next slide, we can look at the effects of humic acid on the influenza virus, which causes the common flu. On table 8, humic acid has antiviral activity, but not as remarkable as the reference product here, which is ribavirin. On table 9, when you look at humic acid and ribavirin, the efficacy of humic acid is actually higher than it is for ribavirin, looking at H3N2 version of influenza. For Table 10, humic acid and ribavirin numbers are there for your review.